And okay, so we're heading into the final lap here. I'm gonna have one more computer assignment for you to kind of do the kind of analysis that we've been talking about here. And also a little nugget on random variates. And then now the final exam is scheduled for next Tuesday at 8 a.m. And it's good for those of you in person. It'll be same thing as the midterm. You know, in class, you can have a sheet of paper, and you might need a calculator if I ask you a numerical thing. I have posted a kind of a quote sample similar to the one that I had for the midterm. And so you can kind of just get an idea of what kinds of things I might be asking. Okay, so yeah. I'm going to try to get it out today. I'm still, I ran into some software issues, but yeah, I mean, basically it'll be to take one of the models that you've already developed and then do a kind of analysis on it that we've been doing here. So, and then just as a little bonus, I'm going to ask you to implement a couple of random variates. So, like in the last written assignment, pretty much every I was actually quite impressed with the way you did. I mean, basically everybody got like the first two, and almost everybody got the last one, which was a bit of a challenging one. And so basically I'm going to ask you to implement those first two and then use them. So you already have the algorithm or the method, and so it's just a matter of putting it together. But that will be, all that'll be in the handout, which again, I'm going to try to get it out today, later today. Unfortunately, I have some meetings and stuff, so it'll probably be this evening. But I'll post it then. Okay. So just to, I mean, what we're doing is, I mean, in a way, we're only, oops. We're really only dipping our toe into what's possible here. Our limited objectives are very modest. Namely, we're going for trying to estimate the mean of some measure that we've decided. And by we, I mean me so far. And, you know, just to kind of review the process, it's whenever there's something stochastic going on, it's not sufficient to do one replication because you don't know how representative it is. And so we do multiple ones and compute the mean. That's or any other measure of interest. We might be interested in the standard deviation. We might be interested in the maximum. We might be interested in a quantile. I mean, all of those are not only possible, but those are ones which I've used in actual no kidding situations. We're just looking at the mean here. So again, as I said, we're just dipping our toe in. And then the next step from that is that it's not sufficient to just estimate the mean by itself, because you still don't know how whether that's an accurate, how accurate is that? In other words, if we were to do this again, would we get something that was close, or would we get something that was farther away? And that's where confidence intervals come in. And you all know from your stats class kind of what the confidence interval idea is. There are a number of different interpretations, but the most compelling one for me is the frequentist one, namely, if it's based on sort of a quote coverage. So if we're trying to estimate the unknown mean and we compute a confidence interval and we say we're 95% confident, what the heck does that mean? Why is the word confidence used? Basically, the way I like to think about it is this, is that we're flipping a coin that has a probability, let's say, of 0.95 coming up heads. Okay, so you can envision that, a weighted coin, not fair. We're going to flip a coin and it has probability of 0.95 coming up heads. And the problem is that we flip the coin, we don't catch it, it falls to the ground, rolls down the sewer. But we knew it had a 95% chance of coming up heads. So what we do is we declare that it came up heads. And we're 95% confident that it came up heads because we knew beforehand that it had a 95% chance of coming up heads. But we could be wrong. And in fact, if we were to do the same thing 100 times, then 5 times out of that, we would in fact be wrong. If in fact we were right about the coin having a probability of 0.95. Likewise, in a confidence interval, like say a 95% confidence interval, if it is a genuine confidence interval of 95%, that means if we were to perform that same experiment, let's say many, many times, then roughly 95% of the time, our confidence interval would contain the true mean. But 1 time out of 20, it would not. And we don't know if what we just did, we don't know if that's one of the 19 out of 20 or if it's the 1 out of 20. But we're confident because we declare it to be so. Right? That's what confidence is. Confidence is sort of saying something when you don't know for sure. Okay, so that's kind of where we're at. And then even that has a little issue, which I'll kind of touch on toward the end. All right, now, when it comes to simulation analysis, again, I'm still reviewing everything, but just to make sure we're on the same page. There are 2 modes. There are, well, mostly 2 different modes, depending on which part of the simulation we're interested in. If we're interested in the beginning portion, the transient portion, then we do what's called a terminating analysis. That's appropriate in situations where that's kind of baked into the situation, such as a natural ending condition, like in, let's say, a typical combat model will have an ending condition. I mean, it's not, even though it may seem that way in certain operations, there's really no such thing as steady state in that. But when it comes to these queuing models, I mean, a steady state is a real thing. And so if say we're modeling a retail facility that kind of opens in the morning and closes at night, that's typically a transient, a terminating, because we're going to restart in the same conditions. On the other hand, there are factories that kind of run 24/7, or even if they don't, when they shut down at night, they start up the next day exactly where they left off. And that's the steady state analysis. Steady state analysis is typically used when you're making capacity decisions. In other words, if we're trying to decide how much resources we need for, so let's say either a factory, or even something like in the in the inventory modeling that I've been doing, it's really kind of a steady state analysis that they're interested in for that. On the other hand, when they're interested in, okay, what are things going to be like over the next year or 2, then that's going to be a transient one, a terminating one. Okay, so, and we've covered the terminating. It's terminating one is the easiest to do, because you just kind of run it for a certain period of time or until a certain criterion is met. And then the challenge there is actually what the heck you're estimating. Because, and the way to think about that is, when we talked about the delay in the queue, since all the observations are different, what we were doing is we're taking the average, say over a certain period of time of the delays in the queue, and what the heck is that if they're all different? So we're not estimating. I mean, in other words, what is the average delay in queue in the transient period is actually doesn't have any meaning. I mean, I'd have to say, so, what is the average delay in queue of customer number 5? Now that has meaning, that's a single number. But the other one, what we're estimating is the expected average delay of the customers for that transient period. In steady state, what we're estimating is easier to describe because in steady state, there is just one number that's our mean that we're trying to find. But the issues are, how do we reach steady state? Because we typically will not start our simulation in steady state. So how do we get there? And then even once we get there, the data are still correlated. So the way that we deal with that is, there are a number of ways of dealing with that. But the most simple, straightforward, brute force one is truncation. And the method's called replication deletion, but I'm not really fond of that name, but that's what somebody else called it. And so what we do is we warm our simulation up, and then truncate. So basically, we kind of choose a point, and this could be either a time, or it could be, say, the number of observations. We choose that time, and then we basically kind of throw away everything that we've gathered up to then. Why? Because that's basically contaminated. That biased data contaminates our estimate. And so, as you can see, there's still always a little bit left over. We can't completely eliminate it, but hopefully we've done enough so that it actually does get eliminated for practical purposes. And then what we do is we basically kind of run it for a while, take that average, and then and that's 1. Now, in some situations, and actually it turns out in one of our examples, it's kind of like that. Every now and then, and this can't really be guaranteed, every now and then the steady state happens so rapidly, like you get something like this, or even steeper. It's like you're almost immediately there. And in those situations, it turns out it actually doesn't hurt so much to skip the truncation. In other words, yes, there's a few observations here that are kind of contaminating things, but if you run it long enough, they get washed out. So the idea of doing the truncation is, it's not. Sometimes it is necessary, and we'll see one example where it is, and one example where you can get away without it. The issue is often in a case where you don't need it. The issue is how much sort of explaining do you have to do. So if you're briefing this to someone who's sort of familiar with this, and they say, okay, well, when you do the steady state, you always have to have a warm up and a truncation. And how do you come up with that, et cetera, et cetera? And if you say, well, I didn't do that because I didn't need to, then you have to, you have a whole rabbit hole you have to go into. So like the number 30 and the alpha 0.01 or 0.05, it's just something that sometimes it's necessary, sometimes it isn't. Okay, so what you do is you get rid of the bias by warming them up. And then for tally, we have, we just take the one observation. This is one observation consisting of n observations after steady state. And then for time varying, we collect the area under the curve after the truncation point for a certain period of time. And how do you pick those periods of time? We're going to sort of punt on that, but just kind of a boatload. And in principle, if we in fact have reached steady state, then we actually only need to take one observation. But it's but what it is that even though those observations are correlated, if we do take this average, the variance of this one data point is going to be substantially reduced if we take the more we take the average. So even though those averages are correlated, if they're positively correlated and we take a bunch of averages, then the variance of this will be reduced, and that'll kind of help with our confidence intervals. And on the other hand, it's like if we're warming up for 10,000 observations and then taking one, and then warming up for another 10,000, taking one, the way that's kind of wasteful. So once we're in steady state, we want to kind of exploit it. Okay, and then and this is what I'll actually be doing, at least for the Java one. It turns out sorry, for the Python one, let's see, my lack of skill in Python coding kind of, and when combined with Python's not really doing inner classes the way I wish they would. Well, the way that I implemented this in SimKit was to use an inner class that was a sim entity base that scheduled the truncation point, and then when it hit the truncation point, it was able to it would clear the tally stat. And I was able to do that using an inner class, which in Java you do. And it turns out that in Python, they have inner classes, but the inner classes can't access the outer classes the way they do in Java. So I wasn't able to implement it in the same way. And so that just, so in the Python one, we're going to have to do something different. So that doesn't affect anybody in the room, but for those of you doing Python, just, okay. So, just to be clear, unlike the terminating case, the steady state measure, it's a single value. It's not some weird thing that we have to kind of wave our fingers at. If we are in steady state, they're identically distributed. That's partly what steady state means, but they're still correlated. And that's why we have to kind of do this other dance. So we want the IID. To get the IID, we're going to kind of do the warm up and run, warm up and run many times. That's the replication deletion. So one replication will consist of truncating the data at the warm-up period, and then we continue to sample in steady state, and then such as the mean, and that's going to be one observation. And we repeat that independently and get a confidence interval. So, and again, just to be clear about that, in order to have independent, identically distributed data, in other words, a so-called random sample, we need to be conducting the experiment in identical conditions, except for the particulars of the random stream. In other words, the random variables have to be the same, and more importantly, the initial conditions and the protocols all have to be identical. So the protocol here is we start in a particular initial condition, we run it for a specific truncation point, we clear out the data and run it for another specific amount of time. And every time we do it under exactly that protocol, except with different random numbers, then we get independent, identically distributed observations. And so with that, we can do a confidence interval. So So yeah, so now basically, interestingly, kind of back when dinosaurs ruled the world, and I was sort of taking this, it's like once the emphasis was on the math, and so we had to kind of, and as you can hopefully tell, that I still have kind of vestiges of that, but that's a little bit less important than actually the implementation. So now there are kind of two choices one has: one kind of doing it by hand, or having it be roughly automatic. So my choice was, in SimKit at least, there are 4 classes to be used for inner stats. And again, my biggest, well, one of my biggest reasons is just coming up with silly names. Okay, so I wanted a simple stats for time varying and tally, and I wanted them to truncate. So in other words, what they're going to do, so actually the simplest one to look at is the tally one. So with the tally, what's a tally? It keeps getting observations one at a time, blah, blah, blah. And the warm up, the truncation point would be a certain quantity of observations. So let's say I want to run it for 1,000 and then truncate. So that becomes another parameter in this, this is actually a subclass of simple stats tally, which you all know how that works. And what it does is once it hits that truncation point, it clears the statistics and just basically keeps going. So so that's sort of built in. So now the user doesn't have to implement that. And there's a similar one for the time varying, except for there, the truncation point is a time. And the thing is, for that, of course, how do you know when you've hit that time? Well, that's where you can schedule an event, and that truncation event. And then there's a similar one for the collection size. And then this was the tricky one, where see, in this tally, in the truncating simple stats tally, you can just sort of keep track of the count, and then once the count hits there, I mean, I could give this to you as a exercise, but it's a purely programming one. So override new observation when you hit a certain when you hit the truncation point, you clear, and you just invoke that. Very simple. The time one was that was a bit of a challenge, and that's where I had this or the way I came up with it was had to have an inner class that was a sim entity base, and then and it would schedule a truncation event, and that truncation event would clear the stats. That worked in Java because inner classes in Java have access to the outer class variables. And again, as I said, I couldn't do that in Python because Python doesn't support that. So it's like it was, anyway. So in the Python one, I mean, I have the simple stats tally and the simple stats time varying in the truncation ones. And this was sort of my bad, which I neglected to implement the collection one. That's going to be in the next version. And then the Python issues, as I said, with the time truncated one for the tally, I need to come up with another way of doing it. Just I haven't been able to figure that out. So all right, so let's so therefore, what I have, and then on top of that, my Python IDE decided to get wonky on me because I foolishly upgraded it, and then all of a sudden things stopped working. So so I'll have to I'll be posting the Python one later once I get my IDE fixed. But all right, let's see what this looks like. Okay, and this is in the class code for the Java folk. And okay, so first for our entity server, and so it's called Analyze Entity Server Steady State. the heck? Did it just go off or has it been off? No. It just went off. They say about, you know, if Microsoft made automobiles and if you're driving down the highway and it starts to get wonky, you have to pull over, turn it off and turn it back on. Okay. All right, so it's the same, same, you know, we've inter-arrival times. There, okay, 2 servers, so it's the same thing. So, okay, so here I've chosen a truncation point of 30,000 and I'm gonna run it in steady state for 100,000. Okay, so here for the numbering queue, for the inner stats, now say the outer stats, you don't do truncation because those you're just collecting the inner data. So this is all for the inner stats. So I have the truncation one, and I give it the name and the truncation point. And then here's the time varying one. So I give that the truncation point. And then, okay, so now I chose a time truncated tally stat. For these, just for simplicity, but I tell you what, I'm gonna I'm gonna just choose 700 here. So for one of these, okay, so what I've done here is I for the delay in queue, I'm going to use a time truncated one, but for the time in the system, I'm just going to use a count for 700. Change that on the fly. Okay, so so when we run that, and okay, so now notice that what I've done here is instead of I've kind of printed what the run stuff is going to be. In this case, I mean, it took a bit longer than normal, about 15 seconds, but notice that we're doing a boatload of replications here. All right, so now our confidence interval for delay in queue is like 36 something. Number was like 23. Time and system 39 something, and then utilization 98.6. That's pretty high. And I want to let's contrast this with the terminating case where we ran it for say just 1,000 customers. Notice that the delay in queue, all of these were much smaller. Well, not, you know, so the delay in queue is like 27 something as opposed to 30 something. So, you know, why the difference? In this case, the properties of the model in the initial stages is substantially different than the way it is in steady state. And that is typical, but it doesn't always happen. So here's an example where, okay, so here's our transient, and we're looking at the server with Renege's model. If we look, and one of our things we're most interested in is the percentage of Renege's. Here it's like something like 14%. And that's the transient one. So we ran 30 replications of just 1,000 potential customers. But then if we run it in steady state, okay, so I'm running it for 30 replications, truncation point of 10,000 and 50,000 in steady state. We see that it's actually not that much different. It's a little bit bigger, but not by a whole lot. And actually, all these other measures are fairly comparable. So, so this is a case where this system actually reaches steady state much more quickly than the previous one. Now, the dilemma is that you don't know which one you're in. And so, and the only way to discover this is to basically do it both ways. So the point is that you don't know. Sometimes it reaches steady state very quickly, and sometimes it takes a while. Now, run this again. Okay, so let's go back to our entity server here and kind of look at our steady state. And okay, yeah, so notice when in the transient period, it was like 27 something, and now it's up to 36 something. Again, not a big deal, but just to recognize that the transient period and the steady state period have very different characteristics. But there is one other issue here. Now notice the size of the confidence interval. So it's like 36 plus or minus 5.5. So that's a fairly wide confidence interval. So what's going on with that? Well, here's the thing, is that when you, well, first of all, okay, now what can we do if we're not happy with the size of this? Why? Because if we're briefing this, what this means is that this, our actual delay in queue could be anywhere from like 42 to like 31 something. That's a pretty wide range. And so it's like if we're trying to make a decision based on this, that makes it kind of challenging. In other words, what we've done is we've checked all of the boxes as far as doing everything the right way, and we've come up with a solution which may not be of any practical value. So what can we do? What's our option? Yeah, just bump up the number of replications. All right, so how can we, well, let's see, let's make it 50. All right, so now let's kind of do it. I want to save this just to keep track of where. All right, so let's run it for 50. So that's going to take a little bit longer. And now the thing to, here's sort of the bad news on this. So what is the size of the half width? I'll have to wait till this finishes and kind of show what's going on. Okay, so now we went from like 5.5 to 4 something. That definitely helped, but 4 is still too big. So here's the, all right, so what's our half width is this. So we have S over root n times our t statistic, which is like 1 minus alpha over 2, and n minus 1. Okay, so that's our half width. In other words, this, am I sharing? You see this? Okay, so this is our half width. All right, so now what happens, let's assume that everything is copacetic in terms of how we are conducting things. So we actually have independent, we've reached steady state, so that isn't, we're estimating the right thing. We have genuine independent replications. And what happens to this? Well, it turns out that there's something like the law of large numbers. Remember that term? Remember what did they say that in stats? Law of large numbers? Well, they did maybe without calling it that. Law of large numbers means that the sample, well, it's usually applied to the mean. The sample mean converges to the true mean if you take enough samples, right? They call that the law of large numbers, because if the numbers are large, then a similar thing happens for the estimate of the standard deviation as well. In other words, as n gets big, first of all, this will converge to what our true mean is. But S, our standard deviation will also converge to, again, there are mild assumptions, mild conditions for this. They'll converge to actually to a number. That's a, we don't know what that is, but it's some number. And now what happens to t as n gets big? You remember what happens to the student t distribution as it gets big? Normal distribution, it converges to a z, which is just what standard normal. That's a fixed thing. In other words, these two values, let me change color so I can. These two values will converge to some quantity. All right, but what happens to this? What's left? So in other words, our half width decreases as 1 over the square root of n is how it decreases. And unfortunately, that's kind of slow. So the point is that what can we, once we, the way, and this is the way that all of the stat stuff works, once we choose n and alpha, once we choose our confidence and our sample size, then we're stuck with whatever we get. And what we get may not be what we want, because so after all that, the half width still may be too big. So what can we do? Well, and the thing, what you notice here, let's see, let's close that. And what we noticed here was that, we went from 30 to 50, we almost doubled it, but we went from like 5 to 4. And, even if we kind of go, I'm going to talk while this runs. All right, let's even go up to 100. All right, so the thing is okay, what are we doing now? We're actually kind of violating the assumptions of the statistical assumptions of the protocol. In other words, we're kind of running it. We don't like the answer, so we'll run it again. Now, and that's kind of a state of sin, for analysis. In other words, and unfortunately, in certain situations where the analyst has been tasked by a decision maker not to come up with an objective an objective analysis of what the situation is, but to come up with a an analysis which justifies the decision maker's predetermined decision, that's not the way it's supposed to work. And that, so basically what we're doing here is not, in a way, it kind of violates the assumption, the underlying assumptions. So what can one do? So, okay, so we went to 100, we more than tripled the original one, and we're down to like 2.6 something. Okay. So we've tripled our replications, but we've only kind of cut our half width in half. You know, why is that? Well, because it's decreasing as 1 over the square root of n, which is very, very slow. Is there but that leads to the question, is there sort of a statistically valid protocol for doing kind of what we're doing in an ad hoc way? And the answer is yes, which I won't talk about today, but that's sort of the topic for tomorrow. And that's kind of the, in other words, like, you know, it hurts when you go like that, don't go like that. So if we choose our sample size and our alpha, we're stuck with whatever we get. So don't go like that. So what is it we can do? Well, why did we choose a confidence level of 0.05? That's not part of the statistical methodology. That's saying, okay, this is how confident we want to be. And maybe it's 0.05, maybe it's 0.01. I mean, those are the two. It could be anything you want, but those are the two basic choices. So what does that leave? So is there a protocol by which we can have the kind of the size of confidence interval that we want and not the one that we get? And the answer is yes. So watch this space. Do I have anything else? Okay, I think I just have all right, so these are the two examples that I did, and then the two lingering issues are how do you figure out the warm up? That's one of the biggest problems, and then are the confidence intervals tight enough? And that kind of in the case of our Renegg model, the confidence intervals seem, you know, pretty tight. In this model, they're not. In this model, they seem excessively big, and so we're going to deal with that tomorrow. Well, that's all I got. So you can owe me a couple of minutes.
Sir, I did have one quick question. I think I caught the tail end of you speaking about the final. You mentioned 0800?
Yes, on Tuesday. That's what I wouldn't have scheduled. I normally they're scheduled during the normal class times, but this time they did it at 0800. So, and you know, if particularly for the remote folk, I mean, if there's some rescheduling or something, adjustments that need to be made for that, I'd be happy to accommodate that.
Thank you very much.
Okay.
Thank you.
Follow-on question to that, sir. Is it roughly an hour like the midterm, or is there a longer time frame for it?
Well, that's okay. That's a good. It's been suggested that the in-person folk don't have another final that day, so we could have it during the normal class time, or would you rather just get it out of the way? Up to you. All right, let's talk about it tomorrow. You know, think about what you want. I'm fine either way.